Okay, so now let's talk about continuous distributions. The thing is that sometimes random variables are not discrete and instead they are continuous. In that case, we say their values are measured instead of counted. Okay, just like the temperature or the height or the average income and so on and so on. There are several things that are by nature continuous or having very huge sample space. The sample space contains so many values. Okay, so in that case, if we are having a continuous random variables, we typically say they have a sample space that is an interval. Okay, just like if we are talking about temperature of our classroom when the next lecture starts, then x is probably within 0 to 50. So that's some natural, reasonable temperatures. Okay, so as another example, suppose we want to consider the number of courses taken by a student in this semester. Okay, then xi is the number of courses taken by student I. That's obviously discrete. It's 5 or 7 or 2, etc. But if we want to talk about their average number of courses, then especially when n is large, we know possible values. There are a lot of possible values, and basically they form an interval. Okay, if we ignore those tiny gaps between values. So with this example, we basically say a continuous random variable is a very good approximation for many discrete random variables. For this particular average thing, we know if we really want to count, the number of possible values is still finite. We can still count all those values as long as we know n, as long as we know possible values for xi. But to do so is so tedious, and that's why in many cases we would use a continuous random variables to do an approximation, to say roughly speaking it is random or it is continuous. Okay, so that's the idea. Okay, so let's understand some technical things. Suppose x is a number randomly drawn from 0 to 6. Now let's start with this technical example. Then that means I'm going to generate x by randomly put a number within 0 to 6, randomly drawn number from 0 to 6. Or I can say I have an interval and I'm going to randomly point at a point. Then that's my random variable x. Okay, then in that case, I probably want to ask the first thing. What's the probability for getting x to be 2 or any specific number? Turns out that the probability of getting exactly 2 is 0. Okay, why is that? We know within this interval, there are infinitely many numbers. Okay, and because we are randomly drawing one number, the probability of getting any number, every number is the same. If that number is positive, no matter how small it is, then when we have infinitely many numbers, the total probability would be greater than 1, and that's impossible. Okay, so that means mathematically, all those points can only have 0 probability. Okay, so technically we would say the probability for x to be any number a is 0 as long as x is continuous. So sometimes some people would feel that this idea is not so reasonable. But anyway, that's not really important because in practice we also don't care about the probability for a random variable, continuous random variable to be a specific number. So if you can understand, that's good. Otherwise, just forget it. What we really care about is the probability of getting no greater than 2 or no less than 2, something like that. We care about the probability of an interval instead of a point. Okay, so we want to talk about this kind of probabilities. If we ask you, okay, I'm going to randomly draw from 0 to 6, and I ask you what's the probability for x to be less than or equal to 2, then Well, 0 to 2, 2 to 4, 4 to 6. We know 0 to 2 is 1/2 length, 1/2 long, sorry, 1/3 long of 0 to 6. So obviously this probability must be 1/3. Okay? Similarly, if we ask you the probability for x to be less than or equal to 3, intuitively we say it's 1/2. For x to be greater than or equal to 4.5 is here, so it's 1/4. For x to be between 3 to 4, we know it's 1/6. Okay? So basically, we can have a few conclusions now. A single value has no probability for a continuous random variable, but an interval has a probability. And when we are randomly drawn for a value from an interval, then given a subinterval, that probability for the value to come from that interval, subinterval, is just the relative length of that subinterval. Okay, so the previous random variable x is special. The thing is that all the possible values are equally likely to occur. In practice, many variables are in this way. Okay, then we say that kind of random variables are uniformly distributed, or we say they follow a uniform distribution. We use a notation x follows a distribution, and in this case it's uniform between A and B. So that means x is uniformly distributed in A and B. Okay? And then the likelihood of any possible value must be 1 over b minus a. Why is that? Because the total probability must equal to 1, right? So we know we are talking about a random variable. If a and b, the distance of a and b gets larger, then the likelihood of any possible value would decrease to make the total probability becoming 1. Okay, finally, if a discrete random variable also has this property, for example, rolling a fair dice, rolling a fair coin, we say it follows a discrete uniform distribution. No, but when we only say the uniform distribution, we are talking about a continuous one. So when do we use uniform random variables? One typical reason to use that is when we want to collect a random sample from the population, because we want each entity to be selected with equal probability. Then we need to use uniform random variables. Okay, so sampling is some topics to be discussed in later courses and later lectures, so let's stop here. But in practice, there are also some continuous random variables that are not uniform. For example, suppose we are talking about temperature, or we are estimating or predicting the temperature for the next lecture. Then capital X is more likely to occur in 20 to 30, obviously, but not so likely in 10 to 20, and very impossible to be within 0 to 10. Okay, so we can say that, well, the likelihood of X in different intervals are actually different. And that happens in many cases. So for that kind of non-uniform distribution, again, we want to describe that continuous distribution. And then the idea would just be the same. List or describe all the possible values, and for each possible value, assign a likelihood to it. So that's the idea of probability density function, or abbreviated as PDF. Typically, we use small f to describe or to denote a PDF. So what's that? That is a function mapping a possible value to its likelihood. Okay, so we say things carefully by saying that's a likelihood instead of a probability, because for each possible value, the probability for that value to occur is 0. Right? So we say likelihood instead of probability. Okay, coming back to here, we say that we use likelihood to denote the likelihood for that value to happen. So that means if f of x is larger, then the likelihood or the probability for the random variable's value to be around that particular value is higher. Okay, so let's use the temperature thing as an example. So here we are having 5 different intervals. Within the interval 20 to 30, we have the highest likelihood, okay, which is 0.05. For the two intervals 10 to 20 and 30 to 40, the likelihood is lower, and that's 0.02. For the last two intervals, the likelihood is very small, it's 0.005. Okay, so again, I'd like to emphasize that these values are likelihoods. If we really want to calculate probabilities, then we need to do some more things. Okay, but conceptually, the higher the PDF, the more likely the outcome is there. So basically, it's more likely for the value to be here, for the temperature to be here. Not so likely here, and very unlikely to be extreme values. If we really want to calculate probabilities, then we need to have a subinterval. And then in that case, basically, we are still using the cumulative distribution function or CDF concepts. Given a PDF f of x, given those likelihoods, if we want to calculate the probability for capital X to be less than or equal to small x, then given x, what should we do? Basically, technically, we do an integral from the lowest possible value to the given value x, and we sum up all those likelihoods. Okay, so then we are doing the same thing as we did for discrete random variables. It's just that previously things are discrete, so we do summation. Now we do integral. Integral seems to be difficult, but we are not going to require you to do that. For here, we're just going to illustrate you this concept. So you may want to follow the calculations or derivations here, but afterwards, when you need to do the calculations, computers will help you, so don't worry. Okay, coming back to CDF. Basically, when we are doing integral, what we are really doing is to find the area below the PDF. So let's see some examples here. For example, if I want to ask what's the probability for x to be less than or equal to 30, 30 is here. So basically, I'm looking for the area below the PDF from 0 to 30. So it's this particular area. I can divide this area to 3 pieces and calculate their probabilities one by one, like this. Okay? So the first region has probability 5%, okay, 5%. The second region has probability 20%, and then the third region here has probability 50%, and the total of them is 75%. So the probability for x to be less than or equal to 30 is 55% by this definition, as the area below the PDF between the lowest value to x. Similarly, if we want to calculate the probability for x to be within an interval, then what should we do? We use the CDF to b minus the CDF to a, right? Because then it's this interval, this particular area, minus this particular area. Like if we want to calculate the probability for x to be within 18 to 30, then it's simply f of 30 minus f of 18. And then simple calculations give us 54%. We can do the calculations for any interval. So if you are interested in that, you may want to calculate and show that the probability for x to be within 20 to 30 is high, but the probability for x to be between 10 and 20 is low, because after all, the likelihood between 20 and 30 is high. So in most cases, we actually will use statistical software to do the calculation. So all we need to know actually is this particular formula, okay, this particular formula. And what we really need is the CDF. For almost all the calculations, we will have the CDF, so you only need to plug in numbers. It's just that you need to know what to calculate and what to plug in. Thank you.